Welcome back to the deep dive. Today we're moving past the basic building blocks and right into the architectural revolution that really changed everything in natural language processing.
That's right.
Last time we explored the transformer architecture, the foundation. Now we're looking at the paper that truly weaponized it for language understanding.
We are jumping into BERT, pre-training of deep bidirectional transformers for language understanding. This is the seminal 2018 paper from Jacob Devlin and his colleagues at Google AI Language.
And it feels like if the transformer was the engine, BERT was the strategic decision on how to use that engine to actually read and comprehend text.
That's a great way to put it.
Our mission today is, I think, pretty straightforward. We need to understand the core mechanical changes BERT brought to the table, specifically how it broke through that persistent constraint of unidirectional models to unlock true contextual understanding.
And BERT is famous for being, conceptually simple, but just empirically overwhelming in its power.
The name itself is the whole story.
It is. BERT stands for Bidirectional Encoder Representations from Transformers. That name is the thesis statement. Previous powerful models were fundamentally handicapped by this directionality problem.
Okay, let's unpack that central problem then.
Yeah.
Before BERT, we had these impressive models, but they all hit this conceptual ceiling because of directionality. What did the state-of-the-art look like right before BERT landed?
Well, there were two major paths. First, you had the generative pre-trained transformer, or OpenAI GPT.
Right.
It was fantastic. It used the transformer and really pushed the idea of fine-tuning the whole model for new tasks. But, and this is the key, it was strictly a left-to-right model.
And left to right, just to be clear, means any given word could only attend to or look at the words that came before it.
Exactly. Which is perfect if you're doing text generation.
Sure, you're predicting the next word.
But if you're trying to understand the meaning of a word in a sentence to disambiguate it, you're losing half the necessary context.
Right. You don't know if launch means a product or a lawsuit until you see what comes after.
Precisely. That context is just crucial for so many tasks like question answering or named entity recognition. If you restrict the context, you're fundamentally restricting understanding.
And what about the other approach? There was Elmo.
Right, and Elmo did try to tackle this. They even called it bidirectional, but it was, let's say it was a bit of a shallow bidirectionality.
How so?
Elmo used what they called a feature-based approach. They trained a left-to-right LSTM, a recurrent neural network, and then a completely separate right-to-left LSTM.
So two different engines reading the text in opposite directions.
Yes, trained independently. And then at the very end, they just sort of stapled the results together. They concatenated the representations from those two separate streams.
Okay, so the different layers of the model only ever saw context from one direction. They only met up right at the finish line.
That's it. It's not deep integration. The core argument in the BERT paper was that this was suboptimal. The left and right contexts weren't being jointly conditioned on throughout the network.
So Elmo is like having two separate consultants read a document, one from the start, one from the end, and they only talk to each other after they've both written their final reports.
That is the perfect analogy. BERT, on the other hand, is like a unified team where those consultants are talking and fusing their insights at every single step of the process.
And that's what they mean by deep bidirectionality.
That's the key. Conditioning jointly on left and right context in all layers of the transformer encoder all at once.
Okay, so the goal was clear. Achieve this deep bidirectionality. But if the transformer is built on self-attention, why couldn't they just, flip a switch and let it look everywhere? What was a conceptual hurdle?
This is the elegant part. If you just allow the self-attention mechanism to look at every other word, including future words, during a typical training task.
Like next word prediction.
Right. Then you create what's called information leakage. The word would just trivially predict itself. It can see the answer in the input.
So if the model is trying to predict the word cat, and you let it see the word cat in its own input, it learns nothing. It just learns to copy.
It learns to cheat the objective.
Mm.
And BERT's huge innovation was finding a way around this constraint with a very clever pre-training objective.
The masked language model, MLM.
The masked language model.
All right, let's dive into that. This is the core mechanical change. How does masking fundamentally alter the training game?
Well, instead of predicting the next word, MLM forces the model to predict randomly hidden words based on everything around them.
The full context.
The full context. It's inspired by this old psychological test called the close task. The system just randomly picks 15% of the input tokens and, well, masks them. The model's only job is to figure out what the original word was.
And this is what finally lets the transformer use its full power.
Oh.
It has to look left and right to infer the missing piece. It forces a truly contextual understanding, not just a sequential one.
Absolutely, but there was a complication they had to solve. During this pre-training, the model sees this special mask token all the time. But when we go to use BERT for a real-world task, like classifying sentiment,
That mask token is never there.
it's never there. That's a pretty serious mismatch between training and deployment.
Yeah, that could make the model's representations brittle. How did they get around that?
They came up with this brilliant three-part strategy for handling that 15% of chosen tokens. It's what makes the whole thing so robust.
The famous 8-0-10-10 split.
The 8-0-10-10 split. So for the 15% of tokens they selected for prediction, here's what they did. 80% of the time, they replaced the word with the mask token.
Okay, that's the main learning signal.
Right. But for another 10% of the time, they replaced the chosen word with a completely random word from the vocabulary.
So that encourages the model to ignore noisy data and rely more on the surrounding context. Still makes sense.
But this last 10%, this is the most counterintuitive part. They just left the original word unchanged.
Wait, what? 10% of the time, they picked a word to predict and then did nothing to it, and still expected the model to try and predict it.
Sounds weird, right? But it's actually a genius regularization technique.
How did that work?
By sometimes leaving the word as is, the model is forced into a state of perpetual uncertainty. It never truly knows which of the input tokens, if any, were messed with.
I see. So it can't get lazy and just focus its attention when it sees a mask token.
Exactly. It is forced to maintain a rich, high-quality contextual representation of every single token, because any one of them might be the one it needs to predict.
That's clever. That forces the model to be attentive to everything all the time,
Yeah.
which is exactly what you need when you go to fine-tune it on a real task.
It is. That forced robustness,
Yeah.
combined with the bidirectional attention, is really the foundation of BERT's language understanding power.
So MLM gave us this deep word-level context.
Yeah.
But, I mean, language isn't just about words in a vacuum. It's about how ideas flow across sentences. If you're only masking individual words, you might be missing those bigger picture relationships.
And that's the motivation for the second crucial innovation, the next sentence prediction objective, or NSP.
Okay.
A lot of important tasks, think question answering, natural language inference, they demand an understanding of how two sentences relate to each other. And MLM alone doesn't really capture that.
So how did they teach the model about sentence relationships during pre-training?
They turned it into a simple binary classification task. When BERT is pre-training, its input is always a pair of sequences, sentence A and sentence B.
Separated by a special token.
A special essay token, yeah. And for 50% of the inputs, sentence B is the actual sentence that came right after sentence A in the original document. That gets a label, is
Right.
next.
And the other 50%.
For the other 50%, sentence B is just a totally random sentence plucked from the corpus. That's labeled not next. The model's job is to figure out if A and B actually belong together.
So the model is learning to solve two puzzles at once. It's inferring missing words with MLM, and it's inferring sentence cohesion with NSP.
Precisely.
Yeah.
And to make this NSP task work, they had to be careful about their data. They used a document-level corpus, books corpus, and English Wikipedia to make sure that the I's next examples were actually long, contiguous chunks of text, not just random shuffled sentences.
So let's connect this back to the architecture. How did BERT actually represent all of this? Single sentences, sentence pairs, with one unified input structure.
It's a really clever additive representation. Every token that goes into the model is the sum of 3 different embeddings.
Right.
First, you have the standard token embeddings for the words themselves. Second, the position embeddings, which the transformer always needs to know the order of things.
Right.
And the third critical component is the segment embeddings. This is a learned embedding that just says, this token belongs to sentence A, or this token belongs to sentence B.
So that segment ID lets the model tell the two sentences apart, even when they're fed in as one long string.
Exactly. And this unified input representation is what led to BERT's most powerful operational advantage, its fine-tuning approach.
Yeah. Because as a user, you don't have to build a new model for every task.
You don't. You take the massive pre-trained BERT, You add one tiny little output layer for your specific task, like a classifier, and then you fine-tune all the parameters end-to-end on your small, labeled dataset.
Which is a huge departure from the Elmo model you mentioned earlier.
A massive departure. Elmo was feature-based. You had to extract Elmo's embeddings and then feed them as features into a whole separate task-specific network that you had to design and build. BERT just said, no, transfer everything.
Which made using it so much easier.
Exponentially easier and more powerful.
And the empirical results of this whole strategy, the deep bidirectionality, MLM, NSP, the fine-tuning, they were immediate and kind of staggering.
Staggering is the right word. When BERT was tested on the GLUE benchmark, which is a collection of general language understanding tasks, the largest model,
BERT large?
BERT large, yeah, it achieved a score of 80.5%. The previous state-of-the-art was 72.8%.
Wow. So that's a 7.7-point absolute jump. For anyone who doesn't follow these benchmarks, what does a leap like that actually mean?
I mean, in that era, gaining half a point was a big deal. It was often worth publishing a paper. To jump 7.7 points on a general benchmark like that was just, it was unheard of. It basically made almost every existing system obsolete overnight.
And for those token-level tasks like question answering, where bidirectionality should matter most, the results must have really confirmed their hypothesis.
They absolutely did. On the Squad View 1.1 dataset, BERT pushed the F1 score to 93.2, and their ablation studies proved it was because of MLM and NSP. They even tried training a huge left-to-right only model, basically a giant GPT, and it performed way worse on Squad.
Even if they tried to fix it after the fact.
Even when they tried to rescue it by adding a BIL-STM layer on top during fine-tuning, it didn't matter.
So that really proves the point. It wasn't just about making the model bigger. It was about enabling the transformer to fuse forward and backward context during the deep pre-training. That was the real bottleneck.
Exactly. The deep pre-trained knowledge from MLM and NSP was just fundamentally superior to any post hoc fix you could apply.
This deep dive really makes it clear. The innovation came from imposing a clever constraint masking to force the system to use its full capacity.
It forced the transformer to finally be what it was always meant to be, fully, deeply bidirectional.
And it proved that scaling works, that scaling up to 340 million parameters really does lead to huge gains, and that knowledge could be successfully fine-tuned even on small data sets.
It made that huge pre-training investment worthwhile for everyone else in the field.
Which brings us to our provocative thought for you. BERT's fine-tuning approach showed that this pre-trained bidirectional encoder could solve a vast array of problems just by viewing them as a sequence pair task and adding a tiny output layer. So given the explosion in models based on this architecture since then, what fundamental tasks remain that absolutely cannot be solved this way? What problems truly demand a different architectural approach rather than just being another fine-tuning task for an even bigger bidirectional encoder?